us. We thank you for the fellowship of the engineering group tonight and all the technical people. And we are thankful for the opportunity to share information amongst ourselves. Thank you, and guide us as we conduct our affairs which will contribute to the common good and safety of all. We pray in your name. Amen.
An affiliate of the National Society of Professional Engineers. This presentation is welcome everyone to this Professional Development Hour presentation brought to you proudly by the Atlanta Metro Chapter of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. This presentation is brought to you tonight live from Wild Wings Cafe in Dunwoody, Georgia. Before we begin, we'd like to let you know that any opinions presented tonight are solely the opinions of the presenter and not that of the Georgia Society of Professional Engineers, the National Society of Professional Engineers, or any other of its affiliates. We certainly hope you will enjoy tonight's presentation, so sit back and relax. And on with the show.
Good evening. A very special welcome to everybody who is here at the Wild Wings for a face-to-face meeting and those who are joining us on our YouTube channel. Our speaker tonight, a special guest, is John Whitten. He's a PMP certified professional project management professional. Yes, he is the head of his own firm, the Internet of Things.
Things?
I'm getting everything mixed up. The Project of Things. He's speaking to us on technologies that disrupt engineering. Specifically, emerging technologies, disruptive consequences, and opportunities for engineers. He is an organizer of the Internet of Things. He's been a consultant in the area. He helps companies implement technology programs. John.
Thank you very much, Roger. I appreciate it. I don't know how many people are up for this or not, but I'm not an academic. That's not my standing. I like to have interaction and discussion. And so I want to talk about quite a few different use cases that I think have some applicability to engineering as we talk through the proposal. And one way I've done things in the past is use a ball. And if you want to, if that's something that you're interested in and you want to speak on, then just ask for the ball, and you guys just raise the ball up, and then we'll see if you have enough. We'll try to keep things moving in that way. So I'll give the ball here. If you want to, if we get to a case where you want to talk about that use case, or you want to, if it's something of interest to you, either raise your hand, ask for the ball, and I'll call on you, and we'll try to get through that. So again, my background, I've got a mechanical engineering degree from the University of Tulsa. We had it was a small program in Tulsa, a lot of petroleum engineering, mechanical engineering, electrical, and mechanical. We took a lot of classes together, so it was a little more interdisciplinary than some programs. And then I worked at Halliburton Energy Services in the R&D department for a few years, developing some novel instrumentation and control products. Did get a patent on one 10,000 PSI pressure transducer assembly that we worked on. I have organized the Greater Atlanta Internet of Things meetup. That's about 2,000 members. We've been going about 5 years. We meet once a month. But I'm also a part of the International Society of Automation. There's a Smart Manufacturing and Industrial IoT division recently formed. We have about 2,500 members. I'm on the board for that, and I was the program chair. We can see that even in the last 3 years and the last 5 years, just the competition and the factors that are affecting today's enterprise. So what does that impact to the engineering community? We know what it is. It could be jobs. It could be the effect of companies. It could require more collaboration than they've had before. It could change their products, change your services, and it could create all kinds of possibilities that perhaps previously we may not have imagined. So what are the real themes that we think are driving some of these emerging technologies and how they apply to engineering? One of them we think is the increased precision and quality expectations that are put on in engineering products and systems. The other is a shift that we see to system thinking instead of product thinking, and things are much more integrated and interrelated than they have in the past. And we see kind of a shift in, instead of thinking of what we're building and what we're making, to kind of also now look at that experience of the user, maybe experience of the customer, maybe the experience of the worker. And so we've had some perspective shifts maybe from what we may have seen in the past. The other thing that's, I think, interesting is the scale of enterprise and how remote work fits into that. The scale sometimes now is so much larger than what an engineer may have had in the past, where they maybe only worked at one plant. Now they may be looking at 20 plants, and they're looking at a much wider scale of the enterprise. The other thing that we see is the asset lifecycles themselves have shifted. So now a company is not only involved in the design of a product, they may be also involved in the manufacture, may also be involved in the service, or maybe some maintenance on that product. And so we think that's also one of the things that are shifting. So as we go through these use cases and go through some examples, I want you to kind of think of these, and if you want to talk about these as we go through, if you can agree or disagree how these may be affecting driving some of the use cases. So what are the emerging technologies? I mean, I guess we could talk forever about different names for different things. These are some of the general things that I've been looking at that kind of come together. There's the Internet of Things, the Industrial Internet of Things. Those are kind of similar but still different. There's the thought of smart manufacturing, artificial intelligence, machine learning, digital twin simulation and modeling that's going on, data in the cloud, and of course mobile and web technologies. So for example, the NIST defines the smart manufacturing as the fully integrated collaborative manufacturing systems that respond in real time to meet challenging demands and conditions in the factory, in the supply network, and in the customer needs. So what you can really see in the smart manufacturing case, it's typical of a lot of the other technologies. It's not just what happens in the walls of the factory anymore. It's really gotten broader in the scope, and that's a lot of the system thinking that's coming in. People talk a lot about Industry 4.0. I don't know if you guys have heard that phrase or not. Industry 1.0, according to some people's definition, was driven more by steam and how that affected machines. Industry 2.0 was affected more the assembly line methods and the methods of production. Industry 3.0 was really when you got electronics involved and controls involved. And Industry 4.0 is really talking about networks and more data involvement. So you can see a continued evolution. One thing that I like to remind people is that Industry 4.0 also requires the electronics. It also requires the assembly processes. It also requires the power. So it's kind of accumulating, adding to, rather than replacing or taking away. There are a lot of people that are looking to create a certification of some kind and maturity at some point to say you're at an Industry 4.0. I think that's kind of a misnomer. There really isn't a certification plan. It's more of a concept of where people are trying to go and how they're trying to move networks and data into some of those solutions. So in my framework that I've talked about, and I'm sure everyone has a different one, I really have 5 components that I see that are important: instrumentation, infrastructure, integration, intelligence, and interfaces. So interfaces is nothing unusual, except now you have displays and visualization, you have notifications, you have escalation, you have a lot more interaction with users and workers than you may have had in the past. And engineers are involved in some of that as well. Instrumentation is about the devices and peripherals to both sense and monitor the assets. That's always been an area of engineering, whether it's mechanical engineering, electrical engineering, or understanding of the processes. Infrastructure really is looking at the domain, that network, that connectivity. That networks have changed, the infrastructure has changed, but both the device and security management is also a big part of that infrastructure. Integration is something that's moved increasingly now to either on-premise or in the cloud, and that includes data storage and processing. And then the last one was intelligence, just looking at rules and logic and the algorithms for essentially to help convert data into decisions. And so that's another important part. So as we talk through, we'll try to make some examples of some of this as we look at the use cases, and we'll try to highlight some of that. But I believe engineering is involved in all of those aspects, and it's an increasing an opportunity for our companies and the future of engineering. So again, instrumentation being sensors, it's also actuators, it's controls. But increasingly, you find that people look at cameras and images now as a sensor. And you also see people will use sound and language and voice as a signal that's to be processed. And these also come now with edge devices that have a lot of compute capability that are very small, whether it's a microcontroller, whether it's a small Linux box. There's a lot of increased capability now in that instrumentation. Again, on the interfaces, whether it's the mobile, the web, the custom applications, you also see a lot of companies have an increasing use of dashboards so that they can kind of monitor KPIs, whether it's OEE or other measures to see what's going on in the factory. You also have an increased sense of notifications now where you can get on your phone, you can get access to lots of information. You can also show video on your phone or video on the application, as well as, in some cases, you can have it speak back to you. The infrastructure, the technologies that are kind of fitting into that are not only the networks. Now it's increasingly possible to do cellular connectivity on devices. 5G, of course, is low latency options for cellular. Also seeing long-range networks that are coming together, whether it's a low-power, wide-area network that's giving a low bandwidth of data. You can see mesh data. You can see where devices talk to themselves. You can see satellites now that have low bandwidth, but they're able to communicate because of a set of satellites in the orbit. And increasingly, this infrastructure includes device management on a scale of hundreds or thousands of sensors. And then you also have the increased security capabilities now that are required as part of the infrastructure. The integration technologies include cloud, also databases, whether it's on-premise or in the cloud. You see a lot more now where there's dedicated time series databases for coordinating data and when it happens. You see rich data models that are now being done where it's not just isolated data together, but all that data is coming together. Maybe it's in a master data management plan. Maybe it's on a platform like Azure or AWS. And then also you see a lot of integration of open source that's coming in. And then finally, on the decision making, with intelligence, you're seeing analytics that's helping to drive that. You're seeing digital twins, where they're creating models of an asset in mathematical model, so they can try to model how they expect that machine or system to perform. The artificial intelligence kind of breaks into anomaly detection, image recognition identification, and also the natural language processing. So these are just some of the characteristics that are there of some of those solutions. But I think it's really more interesting to talk about examples and use cases, so I thought I would try to go through some of those. And if you guys have one that you want to talk up, you can. Again, we can talk about the instrumentation, infrastructure, integration, intelligence, and interfaces, but I think it's probably more interesting to say what are those engineering themes that are kind of driving that. Again, precision, quality expectations, system product thinking, experience type things, the enterprise, and then the life cycle. So one example that we often see in the smart home now is you have a possibility to get cheap devices that you can then have in your home that can then network to a cloud through either a hub or connected directly to the cloud on your Wi-Fi. And then you can have both an app or you can have smart apps, and you can also develop cases for that. So I don't know how many people have interest in smart home or have some examples for that, but it now creates a whole level of automations now that you can produce and create in the cloud, and you can use the app to see some of those things. Does anybody have experience with the connected home that they'd want to talk about?
I want my sandwiches now.
All right, well, there's a lot of possibilities there that really are opening up. Lately, there's been a move by Zigbee to rebrand and work with Google and Amazon more. They're now making a new version called Matter, which will now kind of integrate products even more together, create more interoperability than there has been in the past. Another thing that you're seeing is that people are creating generic architectures now where they take data not only at the low level, but they also organize it all the way up to the top, to the enterprise, with a lot of the infrastructure and networks. You see increasingly use of firewalls and routers in between, and you see the companies are much more integrated now, not only on the operations side, but also into the enterprise side with that infrastructure. So the opportunities and the challenges that makes for engineers is sometimes there's a little more governance now into how things are done. People are tightening up what switches they use. They're also tightening up the ability to have an open port that you can go in and use. And so security is really coming down increasingly as a way to try to make those systems, even though as they get more complicated, also to make them more secure. As you look at those levels, you really see a change of time frame that takes place. Oftentimes what you see at the levels 0, 1, and 2 happen in hours or minutes, sometimes seconds. But what that does is that now integrates with the manufacturing operations management, which really occurs at days, shifts, or hours, and then up to the business planning level, which could be at months, weeks, or days. So although it's continuous time and the data is driven by time, you can increasingly see that it's not necessarily everything is at real-time fast data, but the time stamping and that incorporation of time is an increasingly integrated part of those solutions. So in the past, we may have seen some data that would only be occurring in the production control area. Now that we see that that's getting into the scheduling of machines, the material and energy control, you can see the maintenance management, the quality assurance. All these functions of the business are now increasingly integrated together, and there's an engineering role in many of those. So that's more of a system thinking impact now, that it's not just one thing by itself. It's how do you get that machine to fit in with your overall production strategies. I guess I don't have to tell anyone that has a new car that there's more sensors and more features there than you've ever seen. As the cars become more intelligent or more smart, then there's more use of radar and infrared to kind of see how close you are to the car in front of you. You're trying to decrease that response time, increase your safety, and so there's just a tremendous number of sensors now that are part of any vehicle. You probably have heard that Ford has been affected now by some of its delivery because of some of the availability of some of the chips and electronics that it needs to produce the cars. You can also see the GPS can be built in, but also another big area of IoT has been asset tracking, and that's where you can see where those vehicles are if you have an entire fleet. There have been some cases where people have done some aftermarket IoT solutions, and sometimes they're built in. I think it was Caterpillar actually built in an app into their logic of one of their construction machines that they required you to check the oil before the vehicle could be started. So they actually are moving now to try to say, how can they protect that machine by requiring a certain user experience of going through and maintaining those cars. So I think that's what's interesting. That's such a large ticket item, but there's just so many sensors there. Now there are some challenges for engineering with that, and we don't have to get into all of that, but just the level of code, the level of complexity, the level of fault tolerance, what happens if something goes wrong, there's a lot of efforts that are required in those cars. The other thing, though, is as you look at self-driving cars, is it's not only within the car itself, but now people are saying, how can that car connect with other cars? So you say you want a vehicle-to-vehicle communication. You may want to have a vehicle to a network communication, vehicle to the infrastructure, like the traffic lights, vehicle to the cloud, or vehicle even to home, if you want to be able to open your garage door. So there's a whole level of V2X is the communication now. It's not high speed, but it's increasingly communication to say, not only are we dealing with the car, now we're dealing with the highway, now we're dealing with the roadways, now we're dealing with all of that interacting together with increased precision. There is some good research on that being done over at Kennesaw State with Dr. Billy Kihei, if you guys know him. There's also T-Mobile with some of their 5G work over at Curiosity Labs over in Peachtree Corners. They have a test track for autonomous vehicles as well where they have that. So again, this is not just data. A lot of this is system thinking, and it's really going to take engineers to understand how to put together these complicated systems together. This is one I guess I will bring up, but I guess, and this is one of the, people argue whether this is IoT or not. You probably know there are a lot of steam turbines. Traditional steam turbines will run forever. They'll run for days and days and days. In some cases, they'll even run a year or two without shutting down. It's needed to have a very high reliability. And so increasingly, there's always been some case of vibration instrumentation and supervisory instrumentation on those. What's happening now is now people are finding that they can install wireless sensors. So now that you don't have to open up the casing as much to install sensors as you used to, which means sometimes they have a higher level of sensors. The other thing that's happening is not only are you able to look at the data locally, now you can look at that data remotely. So now's the ability to store the data. So if there was a shutdown in the middle of the night and no one was there, then you also now can go back and look at that data in ways you couldn't. Or you can look at it remotely by dialing into that and see that. Increasingly, they've developed not only a single machine perspective, but a lot of manufacturers, GE, Siemens, others I've worked with in the past, have put in monitoring centers now where they can monitor these systems 24/7. And so the expertise is now shifted remotely. They also have the case where they can model what that vibration should be by looking at 100 machines or 200 machines. And so that really greatly increases the ability, the knowledge of those machines and their performance. As you may or may not know, vibration is not a perfect science. Sometimes you're looking more at relative changes in vibration than absolute changes. But it is a good way when you increasingly look at 10 or 20 or 100 machines, you can normalize that. You can get a lot better information about how those machines are running. Again, that all takes engineering to understand those machines and those sensors there. There's also a case where, as you know, the cost of failure, the cost of downtime on machines is increasingly a critical issue. So you may know the PF curve if you're familiar with some of the maintenance, the predictive maintenance concepts. Some of that says there's a point where a fault occurs, there may be a point where you can detect that fault, and then there's a point where it's going to fail. And so the idea is if you can detect it here, you're still earlier than the point of failure, that then you can make an interaction, or can get involved and interact and make some corrective action. So there's a lot of effort to try to say, how can you do predictive anticipation now on things failing? And that's something that requires increasingly engineering efforts as well. It's not just the math. You have to understand the nature of those machines and the nature of failure and understand what's driving that. One thing that they found, for example, is that often you can use vibration early as an early indicator, but you can also use oil analysis, you can use thermography, you can do a plant inspection. Some people have even found that they've done some ultrasonics and an audible sound now to try, or surface temperatures, to try to find a more optimal case of when those things are failing. So again, this is not something that's going to happen by itself. It's going to be unique to those machines, but it is a tool now that will provide a lot of value, and it will be something that engineers will need to be doing. I didn't have a chance to show all of this, but I did do a project at Siemens where we tried to do some autonomous combustion tuning. And so if you know much about the combustion process and emissions, you're kind of you're in a catch-22. If you go too low, your CO2 will be low, but your NOx will be high. If you go too much later in the process, you'll get your NOx down, but your CO2 will be high. So the ideal thing in your combustion tuning is to try to tune it so you're in the middle where you can optimize the actual emissions. Unfortunately, that's not only an element of fuel quality, it also is a driver is the ambient conditions. And what you see right now is there's a lot of manual tuning that goes in, where it may be 2 or 3 times a year that someone's going to go in and try to tune that engine to be as efficient and emission-free as you can. So there are some efforts now to try to optimize that and try to make some of those changes autonomously using some mathematical models, some neural networks. And so everyone wants to reduce the emissions, but it's going to be a lot harder work than some people realize to actually get to that optimal point. This is another instance where we had a project with a power plant where, as you may know, there's a combined cycle scheme that is an engineered design where you have combustion turbines where the firing temperature is around 2,300 degrees, and so that air is going to be hot enough to spin a gas turbine. You can also recycle that in with the heat recovery, and you can drive a steam turbine. But what you typically find is that there is the normal process is you start up the gas turbine, you hold the turbine for some time until you get things warmed up, and then you'll start up the steam turbine to get the load. Now, increasingly, as they do models, as they understand that more optimally, they're able to find improvements that they can make those closer to being a parallel startup. So we did do a project on a 2-on-1 with Siemens, where we were able to actually pay for the system in about 10 months' time because of the fuel savings. So again, using that mathematics, using what you know about the engineering of those processes, being able to have that fuel savings not only helps you reduce those costs, but it also helps you get to that full load faster, which helps you on your market conditions of creating power. So that's another example where it's not going to be just the math by itself. It's not just going to be the data. It's going to be taking that, doing analysis, and understanding those machines enough to drive that. As an example of the asset lifecycle management, I was just going to, we know the general 4 phases are procurement and construction, operation and maintenance, renew and replace, and then plan and design. Increasingly, what you see is that what you do at the design phase, that information needs to follow the entire life cycle. And you need to follow what that information is. So, for example, in a pipeline, you really need to keep track of a lot of those characteristics of the pipelines that you put in, where they were put in, the size, the thickness, the type of material. Increasingly, you can do inspections now where you can analyze the performance by sending in pigs or instrumentation through those to assess that. And you can now have a higher accuracy of knowing how the pipe was made now that was well beyond what you knew at the time when the pipe was originally made. But now they plug that into risk models where they're able to say, based on this condition of the pipe, what is the likelihood of corrosion, what is the likelihood of other threats, and then you can evaluate your renew, replace, or retire strategies, not just based on the inspection, but based on some risk models that you now have of those pipelines. So increasingly, this is going to happen with more and more products. Rather than just seeing it, the engineered product after it ships, now you're going to have, there'll be some people that will have opportunities to continue to service that equipment, and they'll need to even know more about that equipment than maybe was needed at the time, to manufacture it. Another example, how are we doing for time? Is this good? Is this interesting? Do you guys have any comments or thoughts or so? This is another example that, again, I'm trying to keep it somewhat generic, but there is a county in the Atlanta area who has put in a large-scale water monitoring system now, where they're able to monitor their water use, both at the consumption as well as from the lake all the way in. So now they can better plan their watershed use. And what you're finding now is that they have a larger network now where they probably have 300,000 sensors that are connected all together as part of an overall network. And what that means is that now when you have water coming to a storage facility or to a reservoir, you now know how much is coming because you've been able to measure some things along the way. You have other cases where you know what the demand has been, and so you can also see where that is, and you can maybe anticipate ahead of time. So what people have find that helps them to do is it helps them avoid some overflow situations because they have more time now to act than they would have had before. Again, they can also, just the scale of that is something that would just be hard to have processed in the past. But now with some open SCADA technologies and some other historians and dumping data into the cloud, now they can get even ahead of some of those actions. They can also look for cases where there's leaks or other problems, and that can also help them in that. And so again, it helps to improve those operations at the micro level, but also it helps because there's such a higher expectation now of water quality, right? You can't just tell someone, let's boil the water today or for the next 3 days. People just increasingly find that unacceptable. So it's valuable to try to improve that quality, improve the performance. That's helpful. I'm sure there's several that probably could speak to this as well about the whole revolution now of the exchange of data, engineering data, with the building information modeling that's going on. So again, you're looking at the entire life cycle where you're looking at a conceptual design, the detailed design. You can do analysis on the detailed design of how different things work together. You can document that and have that documentation available for fabrication or construction. You can use 4D or 5D models now as you build that. And so that's a much more data-intensive exercise, more of an integrated exercise than it's been. What's also interesting is how now that not only affects the logistics, but now it gets into the operation and maintenance of the building. Now, because you know enough about that, you have that data at hand, it's a lot, you can maintain those buildings and operate them a lot safer than you would in the past. This is a cold chain example, and I'm sorry, it's probably not too legible on the wording, but essentially it's the farm to fork scenario, right? So now there's an increasing desire for cold chain, and they say, how do we monitor our food from where it was farmed all the way until we get to the customer? So what they find is that the continued growth in the population, that I think they said we're going to need 50% more, 50 to 70% more food than we have now. And there's no way that we can reach that just by expanding the farms. So what people want to try to do now is, can you use the cold chain? Can you avoid spoilage? Can you track that tomato all the way from the farm? Can you keep it cold in the transportation as well as in the processing? And so there's an increasing desire there for both the quality of the food, but also reducing the spoilage of those products, so it will drive more volume for us in the future. Almost through. I've got a couple more here. One of the things that's interesting as well is how, when you look at the connected worker, how much that technology has changed. Now you can look at a fireman, for example, and in some cases in their helmets now, they can get a visual view where they can see maybe an edge detection so they know where they're walking. They may also be able to get a hotspot ID so they can see areas of other interest, or they may be able to see the thermal edge of things because of the night vision. So what you see here is the thought now is saying, how do we make that worker safer? How do we help them do their job? And you see how that drives a level of technology that probably hasn't been used before. They even have communications now, and they also monitor the heart rate, the oxygen and things in the helmet itself. And so then the captain can monitor and say, wait a minute, he's getting alarmed. Someone's maybe under stress. And maybe if you know where he is, then someone else can go and help him. So that's where another whole new technology that we probably wouldn't have thought of, 10 years ago. There's technologies now with heads-up displays. There's also, for example, now because of the barcodes and RFID and some of that's gone into packaging, that Now, if someone needs to go and find the package, the package can actually help them find it, right? Because it has information about it that you can track, or it may be an ID that's on the package. So that's helping a lot in the warehouse and the distribution and those applications. A couple more examples, and then we'll open up some questions. This is just a project you might be interested in, where Georgia Tech worked with out in Savannah, and what they found is that they wanted to track the flooding, and so they were able to put in some wireless sensors, some long-range battery-operated sensors, and now they can track the water levels across that whole area now of Savannah and the Gulf. So now there's a lot more precision in knowing what that is, and it's a lot more real time now, so they can kind of see not just a general warning, now they can give a much more precise warning at cases where the water is an issue for travel or for evacuation and the like. So that's a Georgia Tech project where they were able to monitor those with that. Another Georgia Tech project that was done, they reclaimed that area of campus to be green space, and now they've installed portable sensors there as well to look at air temperature, humidity, soil moisture, water depth and pressure, wind speed, gust speed, rain amounts, CO2. And so now you know the conditions of soil, water, and climate in ways that you never could before. And now if they want to map and see how that's interacting, they can also see that on the campus. But again, one of the things that's interesting with the sensors is how they get they're increasingly multi-sensors. And so it's not just a single variable, but you're seeing lots of variables together. Here's a case where someone has created a sensor for your swimming pool. You can throw this item in your pool, and with an app, you can communicate with it, and you can find the pH, the chlorine, the alkalinity, temperature, the UV, a TDS hardness, and some measure of cyanuric acid now that's in the water. So now you get not only the physical characteristics, now you can even get some of the chemical characteristics of the water. So how does that help, right? Well, it helps you know if there have been accidents in the pool. You're not just waiting a certain amount of time until you're able to clear the pool and reopen. Now you've got actual data that you can use, so you can look at that even in a more detailed way. You can monitor that process. If you're putting in too much chlorine and you're not maintaining the balance of the pH, now you can see there's a lot more intelligent ways to do that. So maybe you're reducing chemical use. Maybe you're helping those that are affected by having too much chlorine in the water. So these kinds of things that you can do now at a consumer level, you can also do in your chemical processes as well. And you can see there's opportunities now with that increased instrumentation to make a better process. The last one I'll just go over is I think many people know that Puerto Rico was recently hit by some storms, and it really caused a lot of disruption to their power grid as well as some of their communications. They now have gone with a company now that's put in a low-powered, long-range, wide area network connecting lots of different points together. So now they've got battery-powered sensors that they have in different places at some hotels, some restaurants, and some of the cell towers. And now you can communicate and get the status of those in an integrated way across the island without the overhead that you need to have to have that powered. And so there's a company that's here locally that's been an advisor in helping this. And you can just see, especially in the developing world where they don't have the money to put in a huge network, this is really a wired network or a cell tower network. This is really a way to get more data together than they would have had. So again, I hopefully try to help you this framework as you look at these things, look at the instrumentation, the infrastructure, the integration, intelligence and interfaces. You can kind of see that there's opportunities for engineers throughout those processes. We could talk some more about this if you want, on what you need to have the people on your team, or maybe how you could do a project. But let me just ask, which applications did you guys find interesting, or which ones did you think are ones that you see?
Want to ask a question? You
Turn the mic on.
Turn that one too. On that side. Pass it on down. Anybody wants my pencil?
Is this on?
Yep.
Okay. I especially like the one about the connected cars and the connected electricity. You know, where you have the whole Internet of Things, where you have a washing machine that says, "Hey, I'm going to be using this much electricity." With the cars, with both of those, where you're expecting essentially thousands, hundreds of thousands, millions of these relatively small devices that are going and sending out information saying, this is what I'm about to do, or this is what I'm going to do. The thing that I keep looking at is if you have somebody who is intent on being a bad actor. So in other words, you have potentially, say, another government or a terrorist organization who says, okay, I want to disrupt stuff, so I'm going to go and I'm going to buy 1,000 of these chips, put them in my car and drive down the street, and then there's going to be no car that's going to be anywhere near me, because they're going to think that I've got 1,000 cars driving down the street. Or maybe they go and they put it in a backpack and drop the backpack off at a half a dozen or a dozen different major intersections. Again, saying the same thing. You got 1,000 cars here, nobody should go. So how do you handle this security of being spoofed by somebody who actually goes and buys the legitimate chips and puts them out there?
Yeah, so what some people have done, and I think I referenced the over-the-air activation. So now increasingly people are making sure that there's some level of communication to those devices. And so they're now sometimes are building security into the chip itself. So there's some unique passcode in that device that is not necessarily observable by looking at the device itself. And so then they use that signature so they know exactly the device they're talking with. So that's one take they're doing. The other thing that I think is always interesting too is the way cars are built now with the CAN bus. I don't know if you may have heard of that. Someone now can plug in and do a diagnostic code using the CAN bus, but there are ways to kind of limit what that node itself can do. So there have been some cases of some cars being hacked, but I think they required, how would I say, a high level of inside knowledge of how those systems worked. But I do think as systems get more complex, what you see is people will build protection systems into that where, for example, on some of the turbines that they have a protection scheme, they require 3 different sensors, and they would do voting of 2 out of 3 have to give the same data, to reflect that. Other people are creating soft sensor models where they're saying, we're going to calculate what that value should be in addition to what the measured value is. So then if you lose that sensor gets hacked, you can compare that sensor to the expected value in addition to just the reading itself. So.
Okay, we have a couple items from online.
Okay.
One, Tom says, fascinating applications, pool water, combustion optimization, combined cycle power plant, water distribution network, et cetera, loved it all. I don't know if you want to comment, otherwise I got another one.
Okay. Yeah, again, I don't think these things all come from a tradition that engineering has had. So I can say some of these things were probably done 20 years ago, but the cost of doing them today versus then, the scale, the precision, those things are all changing. So some of these things didn't just happen 3 years ago, but they're continuing to evolve as the technologies make that available. Next question.
Okay, the next one is from Bob. He says, can you talk more about the gas and steam turbine correlation?
Yeah, so essentially So as you probably know, there is a need in a steam turbine to protect it from having water go inside the steam turbine blades. You're trying to avoid corrosion. You've got expansion effects of high pressure and high temperature. So there's a lot of cases where you're going to divert that until it gets to a certain saturation temperature. And so a lot of that is a matter of sequencing on when to turn that on, but also being able to make sure you have the auxiliary equipment as well started up to support that. So you can contact me. We can have some more discussion if you want. It's an increasing capability where plants need to be able to ramp quickly and also need to be able to shut down quickly.
And also, when have so many things connected, that's awfully tempting for hackers. For example, they might want to hack into home, see if you're in and try to break in, or try to screw up your utilities. You may have heard of hackers getting into baby monitors.
Again, that's why I think you have to look at it from an engineering standpoint. You've got to say, where's that risk coming from? Where are the points that you need to harden or toughen up? And then also, what do you need to do so that if they do get in, that they can't totally destroy something? So I think that it's all going to require a level of engineering analysis and thinking that is, I think, going to come as much from engineers as from other people.
Yes. Am I on? Mm-hmm. How is the application of Internet of Things related to, I remember talking a little bit about water treatment, water monitoring, but as far as flow control monitoring and redirection of water, stormwater treatment, can you address that a little bit? And most importantly, the method of technology used to communicate is 5G now, and addressing it from the Atlanta area.
Yeah, so one of the things that I think we all have to acknowledge is that the cost of automating all of your valves, all of your operations is pretty expensive. Not only do you have to have the motor-driven valves, you also, some of these can be pretty large equipment. So there are a lot of cases where you do want the operator to know and how maybe they can divert things across different channels, or maybe know where they can, where they need to act to that. There is some communications architecture that uses the internet going to the cloud, and then you can use that to communicate. There's also, you can do some dedicated lines as well. But there are some differences between the infrastructure, moving that data around, from the instrumentation that's actually doing the actuation and the driving of those. I don't know if I fully answered your question, or you have a follow-up?
Is it being applied primarily in the Atlanta area now?
Yeah, so there is, for example, up in Lake Lanier, there are some people there that are trying to apply some of that to preserve some of that watershed as well. Yes?
Yeah, I've got a question. Have there been any studies related to the electromagnetic interference with these devices on so many?
So a lot of people have seen that Wi-Fi now is typically going to 2.4 gigahertz, and you can see that there's a lot of sites that are cranking that up a lot higher now. And so what that people are doing now is sometimes they're pushing now to a 900 megahertz frequency just to try to avoid that interference. So there are some cases with the signal processing where they will do a phase shift on the signal as well to try to be more tolerant. I think the key there is that you don't look at the data that it's all coming in once a second. In some cases, the data of an engineering process does not change as fast as you might think. For example, temperature. We can look at temperature in this room, and I can tell you it will change over an hour, but over a 2-minute span, it doesn't really change that much. And so the desire to capture data once a second is probably not necessary. You can probably capture it every 30 seconds, maybe even once a minute for a lot of the decision making that needs to go on. There are those that are looking at that low latency and they're wanting to go to 5G. So people are looking to also look at the possibility of doing private 5G networks at their factory or facility. And then that way they can reduce some of the other costs that they've had of networking and infrastructure. Anything else? Any other questions? Yes.
You know, earlier,
Go ahead.
On the asset management slide earlier on with the life cycle and predictive maintenance,
Yeah.
you mentioned that the data back then might not have, the records might not have been there since they didn't predict that they would need all this type of data using now with the new algorithms. So if there weren't the data available, the records weren't in existence back then, wouldn't that uncertainty go into the models, and how would that play out in actually predicting where failures could occur?
Yeah, so for example, in pipeline, just a big example of pipe, I think I mentioned, now because you have a pig that's going inside you can see manufacturing defects in the pipe because you've now scanned it more completely than it was ever scanned before. And so then you can say, is it more susceptible to internal corrosion because of the thickness of the pipe in those areas? Or you can see if there's some manufacturing defects that maybe were present. So that's one of those cases where you know more now than you knew then. Also, the rate of corrosion is now something that they monitor, not only the rate of corrosion, so then they can do some anticipation of when that's going to be a problem.
Okay, so it's not just measurements and algorithms, it's new data that we're taking now, that we're feeding into the new predictive models.
So it's not just that there are new models, but there's new data to take on the system.
Yeah, there's new data at a granularity that maybe you didn't have before, yeah. So I'll just go, I don't know how much more time we have, but.
Freya, your question?
yes, I was reading earlier that there was a solar flare hitting the planet, not a severe one, but what about hardening all this communication against electromagnetic pulses or a repeat of the Carrington event?
Yeah, I'm not familiar with the particular Carrington event, but I think all these things, the more we learn about them, again, it's going to require engineering to know those things as well as look at those models. So I've got a couple of other things just to show you real quick if you want. The one thing that I would encourage you to do is think, who do you need to have on your team as you go through this emerging technology? And I think that's something you probably need to think about as well. So I have a formula of just some of the types of people that you need to have. You need to have someone the curious, you need to have the creators, you need to have the champions, coaches, captains, and catalysts. So I know it's one of those things where engineers can wear lots of different hats, but I think the technology has changed where so many things are now interdisciplinary that in some cases you may need to have more than one engineer based on the different roles. So just to review those real quick, the curious are kind of the people that are the learners. The champions are the people that are the customers. Creators are the doers. Captains are the managers. Coaches are the supporters. And the catalysts are the ones that look at the barriers and things like that. So I don't want to go through that too much, but there's it is important that you kind of look at that as well, that you have a valid team. If you have a team and you don't have enough doers on your team, then I can tell you your team's not going to get very far. You know, if you don't have a catalyst that's going to help you go through the barriers and the objections, then that's going to be a problem. The other thing that I see as a challenge when people do innovation and these emerging technologies is they always want to go to the production project. They always want to go for the gold and do it at the end. You really need to be able to stage your innovation in a series of projects, kind of building up to that. And so we can talk some more about that if you want. The pilot phase, to me, is really where you put the project in the hands of the operators or the hands of the customers, and you see what it's like when they drive. So I think that's an important thing before you go to production. The prototype really needs to have all the functions and features, kind of the minimal viable product that you have to have for things to work. The proof of concept is really where you solve the hard part of the problem. Some people decide that they're going to do a project and they do the easy part first. Well, you really need to do the hard part first, and you really need to prove out the hard part that's needed for your project to work. You may need to do a practice project where you kind of build your team together, you understand your processes. There's some things that people have done that you can just reproduce and redo. And I'd encourage that if you have a new team or if you have a team that's learning. There's the persona project where you kind of look more at those experiences, whether it's an employer experience, a customer experience. And then sometimes, as you all know, there's just the paper project, right? Let's design this on paper first before we commit, to doing it. So again, I'll be glad to talk some more about the meetup or more to talk about myself. I'm glad to connect with anyone on LinkedIn. That's usually my preferred method. I'll just get to that real quick. So it's just John A. Whitten at LinkedIn, and I'll be glad to connect with you guys and help. So hopefully this was interesting to you and makes you kind of think again how engineers can help and gain and participate in these emerging technologies.
Thank you.
Thank you.
Well, John, as a token of our appreciation for your evening tonight and the informative information, this is our famous GSPE mug.
Thank you very much. Appreciate it.
We hope you enjoyed this presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.